This is refactoring recursion. Who has gone to a recursion schemes talk? A lot. Did they pretty much within the first 10 minutes talk about the fixed point? Did it kind of change the whole thing? So that I gave that same talk a year ago, and as soon as I said fixed point, it was supposed to be a beginner's talk, and as soon as I did that, everybody just, you know, the curtain went down, and I had to spend the next an hour and a half in agony trying to say something to a lot of people that were already tuned out for good reason. So I learned something, and that is, you know, you don't need the fixed point thing to teach recursion schemes, because the recursion schemes are there regardless of whatever data type you're using. So I said, here's the big idea. Just concentrate on just using lists, because we all understand lists, and show the recursion schemes that way, and show what different kinds of recursion schemes. And at the very end of the talk, I mentioned fix. So hopefully that'll help. Just doing this for myself, it helped me a lot. So I'm sure you've heard, you know, all the boilerplate stuff, why you want to use recursion schemes. Just the same reason we use libraries for everything else. If it already exists, why rewrite it? Of course, recursion seems like, well, that's hardly even a library. It's just a little idiom. But the fact is, we do things, right? We traverse over lists, summing things up or mapping across them. Or we build lists up from some number that then comes into a big list or tree or something. And sometimes when we get to, like when we're in C and Java, you get a certain point in the list, and what do you call? Break, to get out of the thing. And there's actually routines like that for everything. So that's kind of what this will be showing, those ideas rather than the fix ideas. So I'm going to, first of all, talk about just explicit recursion, which when you first get a book about functional programming, they have you do that until about page 309, and then they tell you, don't do that. So, and then we're not going to do that. We're going to do a couple of them, and then we're going to use fold instead. And then get right into the main part is this whole idea of using library functions to do recursions, and we're just going to go into detail in the different types of recursion. And at the very end, like I said, I'll talk about, you know, because what that does is instead of putting a loop in your function, you call fold or something else. And so you're basically refactoring the recursion out of your functions. And what I'm not going to talk about is refactoring recursion out of your data, but I will mention it at the very, very end, because that's the fix part. And these are like some of the things, hopefully we'll have time to get to all of them, but there's kind of two broad categories of recursion. There's stuff that, you know, traverses existing structures, and that's on the left side, and it's generally known as recursion over data. And just for jargon, you don't need to know this, but, you know, when you're talking to your functional programming friends, it's really going to be cool when you say, I did an anamorphism on co-recursive co-data. And I said that to my cousin once, and he just looked at me like, God, I hate you, Haskell guy. He's a closure guy. I said, I don't know what that means, and I don't care. But anyway, so co-recursion, basically when you're starting the other way, you're starting from like nothing, and you're building up a structure. That's called co-recursion. Just like in all math, we know there's domains, codomains, and so there's always a dual for everything. And that's all that is co-recursion and co-data. There's nothing magic about it. So I'm not going to drop into detail on those because that's coming up. So here, let's get right into it. So this is the explicit recursion that we all have written. And to tell you the truth, sometimes I still write this just because, you know, old habits die hard. You know, I got to train my fingers to always type fold instead of this. But in this, there's two functions. One's summing a list of numbers, and one is doing AND on a list of booleans. So the pattern is almost the same, right? It's saying for the empty list, I return 0 in the sum case or true in the AND case. And otherwise, you know, I deconstruct the list where I take the first element and then the rest of them. And I take that first element and I do some operator, in this case plus, with recursively calling the sum function. And here it's the same thing, the only difference is the AND. So, and that's what we learn to do in functional programming, in any programming, right? We see patterns twice and we say, oh, dry. So let's fix it. What this looks like when you're actually, now here's the same thing, but you're using fold, and we'll show the definition of fold in a minute. But instead of writing that explicitly, you just pass in the plus function and whatever the 0 is. 0 means when you get to the end of the list, what should you put then for the final value of the function application. And here's true. So that's the same thing. And when you're actually calling this, what it looks like is it takes the first element and gives that to whatever function you're passing in, which is plus, and then it recurses, and then goes to the second element, recurses, goes to the third element, and recurses, and then just collapses that down. And the same thing for and. It's the exact same thing, so it just depends, whatever operator that is, it plugs in right there and becomes the spine of the traversal. And then the 0 plugs in here to the right, which some people will say you can remember fold right and fold left from where this is in the tree, which I'm not going to get into fold left and fold right, but I'm sure you've all heard of it. And how do you remember? Well, that's one way, is where the 0 is. In the fold right case, it's at the bottom of the spine of the tree. In the fold left, it's actually the first thing that goes in. But that's actually kind of irrelevant to what we're talking about. So, sorry I brought it up. So length is, here's another one, just one more example. And this was one, even though you're traversing the elements, it's actually ignoring them. It doesn't care what's actually in the elements. It just wants to know the length. So the function in this case says ignore this element. This is the explicit recursion version, and this is the full R version, where you ignore the first element and then just have this n and you add 1 to it. So if you look at the sum, the and the length, it's the same deal. It's just you plug in whatever function that's going on and you go down the spine. And there's actually cooler ways to write this with const and suck, but we won't do it. So here's the definition of fold R. And what it says is it takes a function that is given some type A and some type B, and given those two types, it returns a B. The fold R is then also given a B value, which was that 0 value all the way down to the right of the tree. Oh, I'm still here. Okay. Yeah, this guy, 0 or true, depending on whatever you pass in. And then you're given a list of A's, and what it's going to return is a B. What kind of B, you don't know. And in this case, so the definition, when you get to an empty list, it returns the 0 value you pass in. When you otherwise, you apply the function to the first element, which is the A, that's this guy, or end to the recursive call, which, remember, this whole thing returns a B, so that's the B right there, and then that returns B. So that's basically exactly what we've been looking at for the explicit recursion we've been doing. So we're not going to do that anymore. Everybody promise, right? They'll never write explicit recursion again. And if you do, put it on Twitter and show it. Take a screenshot and repent. But anyway, so these are the recursion schemes we're going to get through in 50 minutes. Good luck. As many as we can, and then we can go to the hallway and do the rest. And I'm not going to read through these because we're going to hit them one at a time. So here's catamorphism, and guess what? Catamorphism is just a fancy name for fold. We already saw the definition of fold, and remember we saw that fold took a function from A to B to B, and a B in a list of A's and returned to B. Same function signature. And I mean, this is the only thing difference is instead of fold here, it says cata L. And by the way, these definitions, I wouldn't use them because I made these specifically for the talk. The ones you should use are the ones that are full-blown fixed point and everything, and they have optimizations built in. So these are basically to make it easier to get the information across. Although this one actually is usable because it really is the definition you'll see like in Haskell sources for fold R. And here's fold R in action. We saw it a minute ago. We just say here's the function plus, here's the 0 value, 0, and 1, 2, 3, and it sums them up. And all the rest of these slides are going to have these little things that say u.t with some sort of string. And this, because these slides are executable, and I make sure that all the examples, the whole thing compiles, it's written with literate Haskell, and then I run the test, and so all the examples work. Because I've done that too many times where actually what I'm showing is not actually executable code. So promise, this actually works. So that's a catamorph. Oh yeah, I said catamorphism literally is from Greek, meaning downwards. So I still don't quite have the intuition of how it's down. I guess it is. You've got this, like a list, unless you're doing a sum of the list. Well, you're collapsing it down to a value. So maybe down makes sense. But, just because it says B there, B could be anything. You could actually take that list and turn it into a different kind of list or a tree or whatever you wanted to do. So, so downward doesn't, I don't know. I don't really get the intuition of downwards, other than when I say like something like sum or whatever. But in general, if you really generalize it, it doesn't make sense to me. Here's another one, and this one kind of shows you the A-B stuff, because that other example, the input A is an int, and the output B is an int too. So I haven't really done used the difference of types. So this one here, I'm saying I'm giving a list of strings, and what I want to get out of it is I'm going to sum them up but turn them into doubles. So first, the function just says, take the string read, and read is the Haskell function to turn something into some data type. And it happens to know that it's going to turn into a double because this double right here, through type inference, it knows that's what this has to be also. And then B, which is the recursive call, and you get 6.6. And there's a whole bunch of other things that you can write with it. For instance, filter. Filter, you're given some predicate, which you're given each element one at a time, and it returns true if you should keep that element in the list or false otherwise, and then given two lists. So as a catamorphism, here's the catamorphism, which is given the A and the rest of them. Actually, you know what, that should say B's. No, that's right. That is A's because this is filter. Okay, that's filter. Okay, so you're given A and the rest of the A's. And it says if P of A, then you're going to do cons the A onto the rest of the A's. Otherwise, you're going to not include that one and return A's. And the 0 is the empty list. And this version is a lot of times when you see recursion schemes used, you'll hear some terms like algebra and coalgebra. And all that means is the function you're passing in is the algebra. So what are you going to do at that point? And what this says is, given the A, and notice it's not even talking about the rest of the list, if that's true, then I take that A and I cons it onto the rest. Does everybody know the word cons? Yeah. Okay, so you're a Lisp guy, right? Yeah. Okay, well that's even better. But they're all friends, right? Yeah. I used to write a lot of Lisp code at one time, so cons it is, and still Catter and Carr and Cooter.
You know the little schemer?
Oh yeah.
Cons the Magnificent.
Oh yeah, right. He's a good guy.
Yeah.
This is just, so the point of this one is just to say, if you see this stuff, you're going to see this called an algebra when you're doing recursion. You'll see it called a coalgebra when you're doing the other kind of recursion, the co-recursion. And this is just a cute little trick because I'm only in, whereas this one I, send in both, the function used both arguments. This is only looking at one. And then because of currying and partial application and all that magic and lazy evaluation of Haskell, this actually works. Don't spend a lot of time on that, but those little things are, I don't know, I find them fun when I finally see them enough times and say, oh, okay, that's, because it makes the code really minimal. And then once again, I run them just to make sure that both versions return the exact same thing. Of course, it's hardly a test case. I mean, two little things, but at least it works for that. Okay, so we're done with catamorphism. Does everybody get catamorphism? Does anybody not get it? Oh, good. Good. Success. Yes?
Technically, isn't the empty list also part of the algebra?
It is.
Like the next argument. So the function and both the argument for function and the argument for the empty list.
Right, right, right. Wait a minute. And for the algebra, it's given an A.
The empty list can be considered like a function from, it's like constant empty list.
Oh, yeah, right. You're right.
Function is just constant.
Right, right. I had that in an earlier slide, but I dropped it out because I didn't want to get stuck in those things. But you're right. So anamorphism. This is the dual of catamorphism. And dual just means, in a way, you turn all the arrows around. And that's why they also call this co-recursion and co-data. Because when you turn the arrows around for something, then you stick co on the front of the name, and then it's all the same thing, but backwards. Or, forward, depending. Like my brother-in-law from Chile. I told him once, I'm going to come down there and visit you. And he said, who said Chile's down? So yeah, who knows which way is forward and reverse. So anamorphism is, it produces, the idea is it produces structures. Remember the general kind of idea of catamorphism is you take some structure that already exists and you fold it down or downward into something else, which, like I said, that actually you can build other things, but the intuition is to fold it down. And anamorphism is the exact opposite. You take some little seed, and based on that seed, you build up some structure. And in this case, since we're specializing to list, you take some seed and you build a list out of it. But that seed could be another list, or anything. So the type signature for Anna is, remember last time you were given A's and you produce B's. Now this time we're given B's and we're producing A's. So for Anna, you're given a function f, and that f, the type is, you give it a b, and it returns a pair of the a, which is the thing it's producing, and then a b, which is going to be the next thing it's going to operate on. And then it's given a 0 value, and it returns a list of a's. So the definition is pretty straightforward, is you apply f to b, and you get back an a, which is the first thing that's going to be built up, and a b prime, which is going to be the next thing operated on in the next call, which you can see that here. You put the a that was produced at the front of the list, and then you recursively call it, and you call f on that b prime, so it's going to continue. And there's another version. This one, if you notice, this will never terminate in most languages. In Haskell, this will terminate because Haskell's lazy and it won't do anything until somebody asks for some data out of this thing. So, but you can also, there's a version, and matter of fact, the version in Haskell's standard library is called unfold R, and it has this exact type signature where it's a maybe. And what that means is, notice it's the exact same type signature, just where this is blank, this has a maybe right here. So it says, on the case of nothing, you're done. Just don't do any more. And otherwise, you do the exact same thing. You put the A on the front of the recursive call. So it's just a way to actually do termination, which turns out to be handy, and you'll see it in the examples. So here's the simplest one, and that's replicate. So the seed is an int and some value, and what it builds up is a list of those values of length, whatever you gave it. And I'm sure you've seen that many times. And so the way you do that is, this is the anamorphism with the tick. Remember, the tick was the one that returns maybe. Wrong direction. Okay. So what it says, the co-algebra is given the n, and it says for 0, I'm done. So return nothing. And in the case of n, I'm just going to return an x and then n minus 1. And remember what happened was that x became the first element in the list that is being built, and then the n minus 1 is the next value that's going to be passed in to the co-algebra or the function that you're giving to the anamorphism. So when you see that it works, and when I say it works, like this definition of replicate is being used here, and this really runs. It's truth in lending. So, and this one I had to do Fibs because I spent, all my buddies are here. We all spent the whole week with Michael Snoyman, who, by the way, is absolutely fantastic person and teacher, educator, and programmer. Learned a lot from him. But he said over and over again, don't use Fibs and factorial in your talks. And of course, over and over again, he used it. So fortunately, that gave me permission to include this. When he first said that, I went, oh shit, I'm gonna have to change my slides. But he did it, so I'm good. So here's another one, and that is for computing Fibs, I have this function which takes a pair. And I start with a 0 and a 1, and it takes a pair. Well, no, that's the 0 case, excuse me. The 0 case is 0 and 1. And so I basically just return the A as the first thing, and as the first thing it's going to be consed onto the list. And then the next thing that's going to be operated on is this pair, which is B plus A plus B. And to use that, you just say Fibs. And once again, this is using the version without the tick, which means it doesn't have the maybe. So in most languages, this would immediately dump your stack. Do a stack overflow because it doesn't stop. But in Haskell, because it's lazy, nothing happens till you ask for it. And here I'm saying, give me the 7th element out of this list of integers. And it does give me the right 13. So, but the idea with anamorphism is you start with something and you build something up out of that. And here's actually kind of a practical one, and that is you're given something, a string of a string, and you just want to break it up based on some character. And there's a million libraries for this, and this is our latest library version. And what it does is it's using the tick version, right? So it says either nothing or just. When you get to the end of the list, you're done, so nothing. Otherwise, you break on whatever that character was, whatever the predicate is. And the predicate is whenever it equals the comma, it's going to break. And this is a partially applied function. This is called a section in Haskell. Have you ever heard of that before? Yeah. Okay. It's just a really nice shorthand, and that's to say that you've already applied this thing on the right, and it needs another argument on the left, which will be given to it when you call P right there. So in break is a library routine in Haskell. I'm going to show you a little bit what this does in action. But the whole idea is it breaks, it drops one, and then returns. And it works. But let's see this is the part that's not a little clear. If you give this string with foo, comma, bar, comma, baz, with this break function, it returns foo, and then the next element actually starts with the comma, so it actually doesn't drop that comma. And so then when I pass that exact value is going here now, to drop one in second. Second is something from the arrows package, and arrows it sounds intimidating, and once you use it, you realize you do it all the time. Which is, in all programming, once you've done it, it's easy, right? It's just when you don't know, it's harder than hell. But that's the same deal with arrows. Arrows just usually means, like if you start with one value, but you have two functions, and one returns one of type C and one of type B, well then it will actually return a pair. And the same thing, if you have a function that will operate on one type, on both, let me see, it's the other way where you come in with two different types, and then you're going to run one function or other, depending on the type, and have one output. But that's kind of the idea of arrows, and that's what this is doing. This says, second means run this function on the second thing of this pair and don't touch the first one. So it says drop 1, which drop 1 is going to get rid of that comma, and you get the next value. So going back to where we were, break broke it up, so we ended up with something with a comma in front that we didn't want, and dropped off that comma, and it worked. But that's anamorphism again. Okay, and one last example, and this is merging list. And the point of this is, like I said, anamorphism, the intuition is building something up from a seed. And in this case, you're actually taking two lists and just merging them. So there's really not, you're building something, you're building a merged list. But in the seeds are two lists. So I think it's important to remember is just because it says building something up from a seed, don't get it in your mind like, no, I can only use little things like ints or whatever. You can give it anything you want, because the functions, as long as they can do something useful and give it back to the anamorphism routine, then you're good. So this one just says, given two lists that are already sorted, return a merge of those two sorted lists. So I call the anamorphism, the one that uses uses the maybe type, and the C for the coalgebra. And the curry part is just so I can take these two lists and it turns them into a pair the very first time. The rest of the time I get the pair explicitly by passing it back here. So that's curry is just for convenience. So it says if they're both empty, you're done. If the left one's empty, then just keep returning the y and the y's until you've unwound the y's and you're done. Same thing for the x's. And here's the real merge, and that's when you have both x's and y's. If x is less than y, then I'm going to put the x as the next thing to return, which will be the thing cons onto the list, and then the rest of the x's and the y's. Otherwise, you do just the opposite. You put the y, because it's smaller, and then the x and the y's. It's a typical one, and there it is in operation. Okay. I think I'm going to skip this because I really want to get to the other things. HighLowmorphism. Great. Oh, shoot, I don't have where that word come from. Anybody know? High-low? What? Yeah, right. Go high, go low, right. That sounds good to me. Okay, until somebody can come up with something better, that wins. But it's all it is first you do an anamorphism, then you do a catamorphism. So it's just the two composed. So there's nothing magic about it, but it turns out to be kind of useful. So, and remember what I said, don't use these particular functions. These are pedagogical functions just to teach. Use the ones from the library, because this one, anyway, I won't explain why. So this one is given, here's the composition. So first you run the anamorphism, then you run the catamorphism. And the arguments are, you have a function that takes an A and a C and returns a C, and you also give this 0C, then that's going to be for the catamorphism. And then this function, a B, and it's returning a maybe A or a B, that's for the anamorphism. The B is the seed for the anamorphism, and the final result of running the whole thing is that C. And I just realized I'm using eta reduction here. I really should have a B in the type signature and a B right here. Not in the type signature, as a parameter right there, and a B right there. You know, you don't need it in Haskell, because Haskell will let you not mention things because it's already mentioned in the type signature. Is everybody familiar with eta reduction? Okay, great. So here is a HighLowmorphism. This is the other one of the two that he said not to do, but he did it anyway. Yes?
I wanted to mention, I looked up in the Oxford English Dictionary the origin of the word HighLowmorphism. It goes back to 1888. Is the first instance of it in the English language. In J. Martineau's Studies Religious, in that definition, It's a doctrine that primordial matter is the first cause of the universe.
Wow. Jeez.
Oh, that's it.
Jeez, that was a couple of years before they invented Haskell. You know? Jeez.
So Wikipedia says it's Aristotle that compound matter and the form, Hilo being a matter.
Yeah.
Probably because it compounds the Catamorphism.
Right. You know, well, it's, you know, if you think about it, if you get a medical degree, you've got to sit around and have all these weird names for everything, and that's kind of what we're doing here, right? So pretty soon we're going to have to go take a test, and that's what, instead of they're going to ask you about spring, they're going to ask you about HighLowmorphism. That would be a day. I sign up for that. Fact. Okay, back to fact. Thank you for that. That was deep. So HighLowmorphism. This is fact. So what are we going to do? This says the C, which is the coalgebra, is going to run first in the anamorphism. So all that says is for n, when it's 0, you say nothing. Otherwise, you return an n, which remember in a anamorphism gets put on the front of the list, and then an n minus 1, which says when we do the next step in anamorphism, that's going to be the next value given to the anamorphism. So all this does is build up a list from n to 0 of whatever whatever the number was. And after it's done building that, and I'm using these terms build imprecisely because that's not actually what happens in Haskell, but conceptually it builds up a list. And then the catamorphism kicks in, and the catamorphism just says go across that list and run the times. So we've got fact of 5 is 120. But once again in Haskell, because it's lazy, it actually doesn't build up the whole list. It waits and builds up one at a time, and then probably starts running the catamorphism and does it more like a pipeline.
Remember the catamorphism called I and the anamorphism called C?
This one's called A because it's an algebra, and the C because it's a coalgebra. And the only reason I probably could have done it here, wrote ALG and COALG, but when I do that on some of the slides, they run off the right side. But I think I'll update this slide for that because I think it'll be clearer. Because the trouble is, then you start thinking the A's are related to the type signature, and in this case, it's not. It's the algebra. Good point. Yes, that's true. And they're just the opposite too, because the A is the algebra for the kata. Yeah. Deforestation. I'm going to skip this too. All this is. Pardon me? Okay, well then done. Great. Okay. Now, all this means is it's an optimization. You know, just like I was saying, Haskell can do this pipeline, so it doesn't really need to build up that intermediate list. It can actually even do more of that, and that's what this version of it does. But let's skip that because there's more. So paramorphism, we're on to our, is this our third morphism or what are we? No, it's our fourth, yeah. We've done kata, ana, hilo, which was I'm gonna use that for now on. And now we're on to paramorphism. Para means beside or parallel with. And I guess why that's called parallel is because this is given an extra element. Who knows why? But this is almost identical to catamorphism. And so I call it, it's an extension of a catamorphism. And the function that you give to it, remember the catamorphism, it was given an A and a B and returned a B. Now it's given an A list of A's, a B, and a B, and it returns a B. And all that list of A's is the current tail of where you're at in the list. So not only do you get the element, but you get the rest of the list coming up. So You can see that here in the definition, and that's, here's the 0 value, here's the A's, and I take it apart, and I pass to the function the first element of the list and the tail of the list, and then just do the recursion. And as usual, when you hit the empty list, then you use the B value. So that's all it is. Paramorphism just means you got this extra thing, which is the cursor to where you're currently working, which can be useful. I don't know, in Haskell they have this standard, in the prelude they have tails. Has anybody ever used tails in production? Oh, really? Really? What'd you do with it? What did you use tails for?
What did I use tails for?
Yeah.
I forget now.
Ah, okay. Okay.
I got used to the tile something twice with map type and then you get the engrams going all the way through.
Oh, okay. Cool.
Rely on laziness to make computer healthy.
Right. Great. I've only used tails in like Project Euler.
I think I used it to search for substrings.
Oh, okay.
So all I have to do is like map is this equal to the end of the string across the whole thing,
Right.
or do it and like do it all.
Oh, okay. Did you patent that? If you work for a big company like Oracle, they'd make you patent it. Right. So tails, if you look at this definition, it ignores the element, but it says for all the rest of them, just cons that on to what's ever coming up, and indeed, you get all the tails. No big deal. But the point of there is to show you paramorphism is really, really simple, because I think catamorphism is pretty straightforward, and that's just a little bit more than catamorphism. But here's the one, sliding windows. We all do sliding windows, right? And we did one the other day in a class, but here's a sliding window. And what sliding window means is, given this list, I want a window that just shows me each 3-element section, which if you look at 1 to 5, that's what it's going to turn into. And to do that is pretty straightforward. So I have the paramorphism, and I use an algebra because paramorphism is a form of catamorphism, a form of recursion, not co-recursion. Geez, that sounds cool, huh? Anyway, that aside, when you get to the end, it's always the B value, and otherwise it takes a look at these A and A's, and it really doesn't care what's in them. It just says, cons them together, say, is it less than N? If it is, you just return B, and there's no more recursion. Otherwise, and otherwise it takes N, which is what you said you wanted in the sliding windows, out of this list, and puts that on to the remaining of the B's. And that's it. So paramorphism is really straightforward. Okay, this one, apomorphism, meaning apart. This one, the main deal about this is the one, break. This is the break loop. When you're in a for loop, when you say break, that's what this is, kind of. But that's all it is, except for it's an anamorphism, which means you start with something and build it up. But once again, that whole stuff about starting with something or tearing it down, I think that's misleading, because you can really pretty much do a lot of this either direction. But anyway, so apomorphism, you're given a function which takes a list of B's and returns a maybe, which once again, that's just so you can say you're done when you return nothing, and you return a pair of A, and that is the next thing that's going to be put on the front of the list after you've done whatever transformation you're doing, and then an either a B or an A. And the either is the part that allows you to short circuit. It says, when I return a right, then I'm done. That's the short circuit, and here's the A's. And remember, the final value of this is A, so you can kind of tell that that's why this is going to be the end, because this one returns a B, and the only thing you do with B's is give it back to this function. So you can definitely tell from the type signature that the right is the short circuit. And then you can see that then in the actual implementation, you run F on the list given to it. If it returns nothing, you're done. If it otherwise it returns just, and this is going to be the first thing, the thing put on the element list for this step. And then in the case of left, you have some B's, and you just recurse. You continue to do what you're doing. Otherwise, if it's right, you're done. So you just take those A's and use that. And these A's could be empty. They could do it, you know, you're the one, this function's in charge of saying whatever that is. So it can be anything you want there, as long as it has the right type. So that one should be pretty straightforward too, because it's just stopping, allowing you to stop in the middle. So here's a useful thing, and that is insert element. So you're just trying to put a particular element somewhere in a already sorted list. So we hear 3 goes into the slot right there. So what does that look like? This says I'm given an element A, a list of A's, and returns a list of A's. It doesn't say anything about sorting, but a little bit it does, because it says ord A, which just means the elements have to be able to be ordered, which means you can use greater than and equal to on them. So if it's empty, it's nothing. If it's an element of one list, well, you're done. So you say, actually, no, you're not done. You're given an X and a left with empty, which then will come around back over here, and you'll get a nothing, which will then stop. And here's where the action is, and that is you have an element, a list with 2 elements, and whatever else is in the end. And you ask, is X less than or equal to Y? In that case, I'm saying to put the X as the next thing in the list, and then put the Y back on those X's, where you took them off here, and return a right, which means don't continue, you're done. So if you have a really big list here, you know, 1,000,000 elements, and you finally found the place to put it in the second slot, there's no reason to keep doing everything else. And when it's not less than or equal to, then you just continue by saying, well, put Y on next, not X, and you put X back at the beginning of the list, and it'll come around in the recursion and do this whole thing again. So that's the short circuit one. Okay, we've got 20 minutes to make it through zygomorphisms, histomorphisms, and future morphisms. And they're a lot harder. Okay, what's a zygomorphism? It is a generalization of a paramorphism. This one I'm going to have to just read, because, okay, this one. I remember this one now. Honest, I read these slides earlier. You guys were all having fun. I missed the keynote. I was busy reading these. Anyway, it's given 2 functions. This F, which takes an A and a B and returns a B, which is like what we've been seeing all the time in catamorphism. And this is a generalization of paramorphism, which is a generalization of catamorphism. So we're still in recursion. It's also given a second function, G, which takes the A. It also takes the result of F and a C and returns a C. And then it's given a B and a C, which are the zeros. And then this is the input list, the A's that are given to the functions, and then the final result of the C. So all it is, once again, all it is, actually this one's actually pretty simple. You take the two zeros, the B0 and the C0, and you create a pair which becomes the 0 element of this catamorphism. And then there's the beginning of this A, which is given to these functions. So you see that F is given A, and it's given this B, and then G is given the A and the B from the last time you ran that, which could be this B, and the C, and runs it. That's all it is. So what can you do with that? It's amazing. Here's one simple thing. How many times have you had to, in a list, say every third element I need to do something to it? So you write this for loop with the I, and it says, I mod 3, do something. Well, you don't need to do that anymore. You can use this instead. So this is, pardon me?
This is the Fibs scheme, right?
Yes, yeah, exactly. I forgot about that. So PM means plus minus, and L means list. You see these big L's on everything, it just means list, because I didn't want to collide with a lot of other stuff in Haskell, and I didn't want to do a bunch of hiding. So I take the zygomorphism, I give it two functions. The first function takes an A and a B and returns a B. Well, I ignore the A, and all I'm doing, this is just flipping, right? B to not B. And so true, false, true, false. The second function is given the A, the B, which is this guy, and a C, and then runs this PM. And PM just says, given the B and an A and a C, if it's true, minus A, else A, and then continue with the rest. So you see it does -1, 2, -3. So this thing here could be anything you want it to be, but that's it's useful. And when I started seeing this, I thought, oh, okay, recursion schemes. I could actually use them. Besides map and fold in that, because that's pretty straightforward. And what is this? Oh, I was just showing the same thing. Yeah, there's the mod 3. Yeah. I just wanted to show we can do mod 3, not just binary. That slide was supposed to be taken out. Okay. Now we're getting this. This is the good stuff. Histomorphism. This means you get a history of whenever you're at a particular point, you get a history of everything you've already done on the before. So if you've already run F on the first element and the second element and third element, you actually get to look at those results and use those. So, and this is a lot more complicated, but it's actually not that complicated. But there's it's just, well, I don't know what to say. Okay, it's complicated. History. Okay, there's this data type, and all this means is when you're at the end of history, you have this value. There's two types, A and B, and this is the input, B is the output. So the end of history, it only has output. It's over. And for each step in history, or epoch, or whatever you want to call it, you have a value that came in, and this was the result, but it also has access to history, which is whatever was done before and at each step. And these histories always have, if it's the end of history, you can get a value. If it's a step, you can always continue to go back. And here's the main function, which actually, that's right, it is simple. Because it's a catamorphism, and we know that catamorphism of everything we've looked at today is the absolute simplest thing. So it just says, given an A and an H is the history, and whatever element I'm working on, I turn that into a step, which is this constructor of a history, and I give it the input value, and then I give that step the result of F, A, and H, and H is the history. But that's also what you're about to compute the next time and the next time and such. So it actually kind of works bottom up, which you'll see in the examples. That part's a little tricky. It's hard to see, but I'll show it in a minute, because this looks like, yeah, I won't try to explain that. I'll wait to get there. And then these are just, this is just an accessor. So the value, to get the value at any point in history, if it's the end of history, it's always just the B, and otherwise it's the B in the step value. So that's just a useful thing. And the actual, now here's the actual definition of histomorphism. And that is, whoops, yeah. Well, history is, it's the end of history. It says that given a function from A to history of A and B, returns a B, and it's given a 0 value, a list of A's, and a B. And all that is you run this history function, which is where the real recursion is going on, the catamorphism, and when you're done, you take the value, which is going to be whatever at the front. Okay, so that's, I didn't understand it, did you? Yeah? Oh, okay. This one it helps to see something in action. So remember, there was this function history, which wasn't the real function. The real one was this one that took the value at the end. But I found it easy to kind of step through history to see what it looked like. So if I give history this function which just says A and ignore the second argument and just show it. So all it is going to turn each one of these numbers into a string. But what you get back from it is the first step, it takes the first one and returns a 1. But that function also returned, and that was where I was showing on the other slide, this thing here, this H and this H, you actually are embedding in it calls to things that have already been done, that are going to, actually, why is this called histogram? This looks like you're seeing what's happening in the future. Now I'm confused. I might have got these named backwards. Anyway, doesn't matter because the other one is the opposite of this, and you can just relabel them to your heart's content and use them. But anyway, so this step, notice it has access to the next step in history, and this one has access to this step and also the end of history. And that's kind of the magic part. And now we'll actually make it do something useful. Oh, there's also, when you want to get to the previous history, when you're in a step, you just grab the history slot. And when you're in a 0, you just return it. So here it is, Fibs again. Come on, Fibs is really useful for teaching. It is, because it has interesting recursive structure. So here it is. Fibs just says, given oh yeah, I was confused because I'm using history, not histo. And the reason I'm using history is because I wanted to actually see all the intermediate stuff. Remember on histo, it takes the value. So it just takes the thing at the top. And so it's just using history and then taking the thing at the top. But I actually want to see all the intermediate stuff. So that's why we don't actually see histo here. So all this is says at each point in time, take the value of the history and the value of the previous history. Exactly what Fibs is. And if you look at that, when you come in here, it starts on 3, which is, hand wavy, 0, 1. Yeah, we didn't cover it. It says on step 1, to calculate this thing, I've got to look at my current value, value of H, which is the history. So the history is this guy. So I'm given this history. So I take the value, and the value is 13, and then I take the value of the previous history. So I take this history and then take the previous, and I get to here, and so I get these two, which become 21. And then it just kind of goes down until you did. But in a way, what happens when you run this, this is the first thing to get calculated, and then it backs up. So it really works bottom up in its execution strategy. But when you write the actual algebra, it looks just like you would write Fibs. This one's pretty cool. When I finally came up with that visualization. Okay. Yeah, class. What would be the big O complexity of this?
Does Haskell use tail recursion?
Yes. What would be the big O complexity? That's a great question.
I'm sorry, O then.
I think so.
And Fibs to compute. However, it seems wasteful in space.
Yeah, there's better. That's what I keep saying about this. Don't use these implementations. The real histogram thing is much better, but this is a good one for learning. But yeah, I think you're right. Just order in, because all you're doing is on the list version, however long the list is, that's how many steps you take. So I think it really is.
You ever use it for anything real?
Me? No way. According to all the things I've been reading, histogram is really useful for dynamic programming. And how many has done dynamic programming and algorithms class? Yeah, okay. So then ask them.
I know that, so Slam Data here in town uses a lot of recursion schemes for all of their compiler for their variant SQL. And histomorphisms are really useful for bottom-up annotation of trees. So, for example, type inference can be done.
Yeah, great, thank you. Okay, we got 5 minutes. Oh man, sorry. You're gonna have to do Futuremorphism on your own. Because we have to talk about fix. Come on, I didn't put you to fix until the very end, so you got to learn about fix. And besides that, there's no way we're gonna get through this. Because this one is, look at that. You do an F of A, and it returns a B of B's and M's A's, and then you do a case on that, and then it goes future across. No way, no way. But this one, supposedly, you have histogram. You have access to previously computed values, which is true. We saw that they were previously computed, and these are somehow going to be your access to future values. Now that is magic. That is definitely magic. But yeah, I'm gonna, because we only have 4 minutes left. So okay, this is a use case, swapping elements of a list, and you just say, here's a stream from one, which just give me a bunch of a list. Take 10 of them after exchanging them, and this is the algebra, which says, in the tail of this list, give me its head, which that's good for, and put that at the beginning, and then the next two things, give me this head of x's, which is kind of magic, and then the tails, which is 2 elements down, and you see it does a swap. But let's just skip this and go on. Sorry. I'm actually surprised. I didn't think I'd make it through HighLowmorphism. So here's the next thing. So we've been talking about refactoring recursion out of functions. But you can refactor recursion out of data. And probably the easiest thing you'll do about 90% of the time is define a recursive data structure, which just says here's a tree, and the one is just because I didn't want some clashes with some other trees I had of A, type A, and the leaf holds one of these, and the binary, the branch, has 2 trees of that same type. What you do is just say deriving foldable. As soon as you do that, you can build up one of these trees, and then you can use fold_r from data.foldable, and it works. So there's also traversable. You can say derive traversable, so you can then start traversing things, and that's it. So use that. Don't ever write fold, and don't use the library fold. Just make them foldable. There's probably a reason to use anyway. That's probably will get you through, like I said, 80–90% of your day job. Occasionally you might need more, and this is the magic part, the fix part, and that is, and I'm not going to try to make you understand this. This is just a boilerplate pattern, but it works. And that is, you say it's the same thing we just looked at a moment ago. We have a tree of A, type A. This is the same thing, except for you also include this R, which the R is kind of standing for recursion. And for leaf, there's no recursion, so it just has an A. And for the binary, it just has R's because there were 2 branches, so they're the recursion points. And you say it's deriving functor because that's part of the magic. And then you just find a type alias, which you say fix of that particular tree type, and that fix puts in the recursion. It just, you put it in the mixing bowl, you stir 5 times, and recursion gets put in. And then everywhere you want to use a leaf or a binary, instead of the constructors, you have some smart constructors, because you don't want to have to deal with this fixed stuff in all points of your code. And then you can build up that exact same tree we saw a moment ago here. That's the exact same thing, except for you've got lowercase ones, so that we're using this thing. And now you're done. You can start using all the recursion schemes. Everything we've shown are now available to any recursive data type. And this is the there's different ways to define these things, but this is a version of doing catamorphism for fixed point types, which is any recursive type, including lists. And for some, you just say the algebra, if there's just a leaf, you just return A. If there's two branches, you just add those together. And actually, this is append those together, excuse me. And you're done. So that's that page right there. That's it. That's the boilerplate, which will allow you to do refactor recursion. Yes?
So if you do it the first way, you just use a recursive data type and derive foldable and traversable, you don't get like zygo.
Right.
Okay, you're just going to get some fold.
You'll get fold and traverse and stuff. Right. But if you need the other things, then the fixed point. Yes?
As far as I know, this pattern doesn't support which are recursive data types.
From what I've read, but I certainly haven't used it myself, you can do it, but you've got to jump through more hoops. But yeah, this particular boilerplate I was showing, you're right. It doesn't support mutual.
It's convenient, so it's what to move around
Right.
to support.
I can't remember. Yeah, sorry. And let's see. That's it. I'm right on time. And these are references. This first one, Tim Williams, that you should definitely watch his presentation. It's got the slides available and the YouTube link. And I put a reference to my slides in the Slack channel so you can get that. But that is a really, really good presentation and uses a lot of advanced stuff. He starts right out with fix. But now that you know what all the recursion schemes are, there's a bunch more. You can get through that a lot easier. And then this is kind of like the classic paper on it, the bananas and lenses. And I'm sure you've heard all the banana jokes about recursion schemes. So that's kind of there. And then my slides are just on my GitHub. And that's it. Thank you.